Now, the theory said the coldest you can get is 240 microkelvin. Now, that's really, really cold, okay? Because room temperature is about 300 Kelvin, okay? And we're talking about getting the temperature down to 240 microkelvin. So we did it in our lab. 240 microkelvin. We did it exactly the same way Steve Chu did. And then we started to do more experiments. We'd start with the molasses, turn the laser beams off, so now the atoms expand. And let's put another laser out here. So the atoms will take a certain amount of time to get there. Mm-hmm. And when they do, they'll light up, and we can measure the time it takes. We saw nothing. 0 atoms here. And then we said, what if we put the laser underneath the atoms? Big signal. The atoms were going so slowly they couldn't make it up. Just gravity. We'd done the calculation. Gravity shouldn't have had any effect at all at the temperature we thought. And we just measured it, 40 microkelvin. 6 times lower temperature than what was predicted. So we were scared. We thought, we're obviously doing something wrong. This can't be true.
Mike and Misha visit Nobel Prize-winning physicist Bill Phillips, whose experiments with laser cooling and optical molasses defied the known theoretical limits of physics. In this conversation, we explore how his laser cooling experiments broke through the Doppler limit and why ultra-cold atoms have opened the doors to new technologies like scalable quantum computers. Please welcome Bill Phillips.
Well, I like the definition that Einstein gave, that time is what a clock measures. And while that may seem a little superficial, by taking the idea seriously, Einstein came to his understanding about the relativity of time in special relativity, for example. So that's the definition I like.
Well, what can we do with time? Like, how do we measure it?
With a clock. So time has become something that is woven into our daily technological lives. The global positioning system, the satellite navigation system that you probably used to get here this afternoon, relies on atomic clocks. There's a constellation of satellites, each of which contains a number of atomic clocks, broadcasting information about what time it is, broadcasting information about where the satellites are, which is the determination of which is made easier by the fact that it's got really good clocks on board, and broadcasting that information to your GPS receiver, which then processes that information from multiple satellites and determines where you are, typically within a few meters anywhere on the Earth. So time in that way has, and time, extremely precise measurement of time, has been woven into our daily lives, because today people hardly go anywhere without using their satellite navigation. In earlier times, before things like railroads allowed us to move distances in short periods of time, isn't it amazing how often the word time comes up whenever you talk about time?
It is.
People didn't worry that much about time. People kept time locally using the position of the sun. But once you had railroads, people had to worry about what the time was in different towns that the train might pass through. And that produced things like time zones. We decided with everyone within the time zone keeping the same time. That's a relatively modern invention. So modern life has required a very different approach to time than was necessary in other times. I spent a year in Oxford, and one of the things that you very often noticed was that the time at Christ Church was different by about 5 minutes from the standard time, and that was because Christ Church still stuck to the old tradition of local time, and so its bells would ring, telling the undergraduates they had to be inside the walls at a different time from what the official local time was.
is it also, I guess, tradition would go like to MIT? I know they have like MIT time, which is 5-10 minutes after. So after the beginning of the class, so I guess
Yeah.
students make it.
Yeah, so social time, of course, is an interesting concept, and I'm afraid I don't know a whole lot about that. I certainly remember those times. We used to say, well, for an assistant professor, we're only going to wait 5 minutes, but for a full professor, we'll wait 15 minutes before we'll leave if he doesn't show up.
I see. So during your career, you've been, I guess, like as I said, one of the big breakthroughs is in increasing accuracy for measuring the time, with specifically working with atoms, which seems like one of the most identical or stable. I mean, identical entities which can be used for that. So, how did you end up working with atoms and wanting to cool them down with lasers?
Well, let me take this question into a slightly different direction. We're talking in the middle of July 2025. It was just a few weeks ago that my thesis advisor, Dan Klepner, one of the great physics figures at MIT and the whole world, passed away. And it was really, he was the one who taught me how to think like a physicist. He was the one who really got me interested in atoms. It was through the research that I did under his direction that I got into the idea of interacting atoms with laser light, being able to manipulate them in a way that has led to laser cooling. But there's another thing that I want to say about Dan. What an incredible guy. People who come to atomic, molecular, and optical physics, what we call AMO physics, from other fields of physics, often remark about how collegial and kind the people who are doing research in this area are compared to a lot of other areas of physics. And I believe that the reason for that is that we have seen as our leaders people like Dan Klepner, who embodies those kinds of principles of collegiality and kindness and generosity toward both colleagues and competitors. Dan Klepner got that from Norman Ramsey. In Europe, I think that's very much the result of the personality of somebody like Claude Cohen-Tanucci, who got that from Alfred Kessler. All of these names are giants in the field that we're talking about right now. And so the way it happened for me was I was invited by Dan, wrote me a letter when I was an undergraduate, said, I looked at your application at MIT, and I think you might be interested in the kinds of things we're doing in my research group. And I went and visited his group at MIT and immediately realized this is where I need to be. This is the right place for me. And we were doing work with hydrogen. Now, hydrogen, the simplest of the atoms. Dan Klepner has had a kind of lifelong love affair with hydrogen. And we were studying hydrogen atoms in a relatively high magnetic field, a few kilogauss. I'm not supposed to say Gauss because it's not an SI unit. So a few tenths of a Tesla magnetic field, holding these hydrogen atoms in a vessel, a glass quartz vessel, and studying their resonance behavior at extremely high accuracies. That was the thing I started doing as a graduate student. Well, after having done a couple of experiments involving that hydrogen maser, very nicely accomplished experiments, we started to get in the lab tunable lasers that we could adjust the wavelengths so that we could make them resonant with an atomic and molecular transition. And I thought, this is the way of the future. The kind of thing that I've been doing, as exciting as it has been, is the past. I want to be in this way of the future, using lasers to interact with atoms. This was the first time that most laboratories could do this because people were selling lasers that you could tune. In the past, you'd have to build your own laser. And by the time you did that, it was hard to get other experiments done. So the technology of being able to have commercially available tunable lasers was a huge change in the landscape of atomic physics.
How much can you tune that laser?
Well, it depends on the laser. These were dye lasers. And today, nobody wants to use a dye laser because it's such a hard instrument to work. But it was all we had back then that could be tuned widely. And so you might be able to tune a dye laser over some tens of nanometers of wavelength, maybe even 100 nanometers or so, depending upon the dye and how good your pump was. But what it meant was that we could tune the laser so that it would excite sodium atoms. In fact, sodium atoms were about the only atom that was available that you could hit with one of these dye lasers, at least a good dye laser that could produce a reasonable amount of power. So I went to Dan and I said, look, I'm finished with these old experiments. I'd like to do something new with lasers. And he said, sure, let's figure out something. So I did what I think was a relatively mundane experiment, studying the collisions of laser-excited atoms. But the difference was it got me into the field. It introduced me to this new technology. And when I went from MIT, where I was, after I did a postdoc with Dan and Dave Pritchard after I finished my degree, and then after 2 years, I went to NIST. At that time, it was called the National Bureau of Standards, NBS. Now it's the National Institute of Standards and Technology, where I am now. And I went with a combination of the background of having done these precision measurements, which, as it turns out, were relevant to precision measurements that were being done at NBS then, and with these new ideas about using lasers to excite atoms. And being at NBS, a place where metrology is the key thing to what we do, I thought about what could I do with atoms and lasers that are going to advance metrology. Now we come back to Dan Kleppner. One of the great things that Dan did was the invention of the hydrogen laser, which he did with Norman Ramsey. One of the best atomic clocks, even now, but an amazing atomic clock at the time that they did it in the early 1960s. So the idea was to use the hyperfine frequency of hydrogen to be the standard reference, the ticking frequency of a clock. Now, the trouble was that the hydrogen atoms at any reasonable temperature are moving really, really fast, over 1,000 meters per second. So how are you going to make good measurements on something that is here and gone in almost no time? And the idea was store them in a bottle. Now, it's kind of amazing that you could take hydrogen atoms and store them in a bottle. I mean, a hydrogen atom, not a molecule, but a hydrogen atom is an extremely reactive thing. And you would think that it'd be a disaster trying to put it into a bottle. But Dan Kleppner's thesis was about bouncing atoms off of surfaces. And he found that you could maintain the coherence of the superposition of the atoms being in the two hyperfine states. You could maintain that coherence even when it bounced off a surface. And that it could bounce off a surface, not stick to the surface, as long as the surface was of the right sort.
But why wouldn't the hydrogen atoms just merge into H2?
Yeah, very, very important. In order to form a molecule from two atoms, you have to conserve energy and momentum. And you cannot do that in free space. It's just, for the same reason why the Earth cannot capture a satellite. You cannot form a molecule with a collision of two atoms. You need a third atom to take up the the energy and momentum. An important fact, and one that we often forgot about over the years. But so the only way you're going to form molecules is if the atom sticks to the surface, and then another atom comes along
Really?
and sticks, and then you can use the surface to take up energy and momentum.
What about just releasing a photon?
Well, there is no photon because
okay.
the atoms are in the ground state,
Hmm.
and there's a microwave photon, but that doesn't have enough energy and momentum
Okay.
because when the hydrogen atom goes into a bound state, that's a lot of energy. They're really deeply bound, so you got to get rid of a lot of energy. Well, another atom can easily take that energy up, but we just don't have any other way of doing it except the surface. The fact that the atoms don't stick to the surface was a really important feature. And so that made the hydrogen maser, which, as I said, is still used as a clock to keep time really well in the short term. But coming back to my thinking when I was at...
how does the hydrogen maser clock work? What's the working principle?
Well, you shoot a beam of hydrogen atoms. So first you start with hydrogen gas. You run something like an electric discharge. I think we were using radio frequency discharge. In any case, you dissociate the hydrogen atoms. So now you've got these hot hydrogen atoms, and you make an atomic beam.
Mm-hmm.
So atomic beams, this was one of the things that made Ramsey's reputation was atomic beams, which he learned in the lab of I.I. Rabi, who was one of the pioneers in atomic beam work. Really invented the idea of the atomic clock. But anyway, so you make an atomic beam and you shoot these atoms into a bulb. Usually it would be made out of quartz, and it would be of a size that it could fit inside a microwave cavity for the right microwave frequency for the hydrogen, which, if I'm remembering correctly, is about 1.4 gigahertz.
This is like a vacuum chamber, quartz vacuum
Everything's
chamber.
in a vacuum. Yeah. So, so this bottle, this spherical bulb, of sort of that size, has a long neck to it, and the atoms go down the long neck and hit the bottle and rattle around inside.
Mm-hmm.
And they can rattle around thousands of times before losing their coherence and finally finding their way out of the long neck. So this was this genius idea that made the hydrogen maser possible. And the key thing is that you have the atoms hanging around for a long time, so you can make a really good measurement. Now, fast forward to my going to...
So it's like trapping by, sort of like trapping by the surface?
Yeah, that's right. Yeah, trapping by putting it into a physical bottle. Today, we trap atoms in all sorts of ways using laser light, magnetic fields, and sometimes we call these things magnetic bottles. Well, this is a physical bottle.
Well, in a way, it's also an electrical, like the wall is just an electrical potential. So it's a cage of electrical potential.
That's right. Just all depends upon the scale on which you decide to look.
Yeah.
But most people would think of this as being a physical bottle.
But the principle is the same as other atomic clocks, meaning you have an external, you're applying, let's say, microwaves in this case, and then you're looking at whether basically you're tuning your frequency to be absorbed by the hydrogen, and therefore that like this is the exact frequency that I'm expecting.
It's a little more complicated.
Okay.
And a lot more beautiful.
Okay.
So in this atomic beam, you select the state of the hydrogen atoms by putting it through a gradient magnetic field that will bend a particular state in one direction and the other state in the other direction.
Okay.
And you focus, as it turns out, this particular case, it's sort of like the Stern-Gerlach experiment where you...
It's like a spin state or...
Yeah, spin state.
Okay.
Because the two hyperfine states of hydrogen are essentially... this isn't exactly right, but it's the relative orientation of the nuclear...
This is basically the NMR. It's the same thing as NMR.
Well, yes, except that we're really working on the relative orientation of the electron and the nuclear spin.
Oh, I
as
see. Okay.
opposed to just
Proton,
the orientation of the nuclear spin, which
I
is
see.
the atom,
Okay. Got
relative
it.
to a magnetic field. In
Okay.
this case, we're at a low field, and it's the relative orientation of the electron spin
Mhm.
relative to the spin of the nucleus. So you can think of it as having the nucleus creating a magnetic field at the position of the electron, and then the electron flipping its spin relative to that. That's an oversimplification, but let's leave it at that.
Mhm.
So you select the state of the atoms by this focusing magnet that focuses the state you want into the
Into the bottle.
bottle and throws the other one away. Now, inside the bottle, the atoms are the bottle is also inside a microwave cavity. It's tuned to the transition frequency between the two states of the
Mhm.
of the relative.
Now, are you selecting the low energy state or the high energy
Doesn't
state?
really matter.
Doesn't matter. Okay.
the key thing is that there's going to be another state.
Okay.
And then what happens is you can, well, I'm trying to think how much detail to go into here. I could, using the microwave field inside the cavity, turn the spins of the hydrogen atom so that they're going toward the other state.
Mm-hmm.
Now, once they're in a superposition of being in the two states, that means that there's a magnetic moment that is rotating, oscillating in the cavity, and it radiates.
Okay.
And the whole thing can happen spontaneously, you see, because you've got this this population inversion,
Mm-hmm.
and or at least a population imbalance between the two different hyperfine states, and that radiates into the cavity. The cavity, in a sense, stores that field and enhances it. And as more atoms come in, they're subject to that field. And what happens is, in the usual hydrogen maser, the thing is self-starting and self-sustaining. As you put more and more atoms in, they are rotated into as their spins are rotated into the state that's radiating, and the thing just naturally radiates. That's why it's
Turns
called
into a
maser, because it's microwave amplification by stimulated emission.
Mhm.
And so you've got this field in the cavity, you've got atoms coming in, and they're going to radiate into the cavity. And so in that case, you do want to be in the upper state because you want to radiate into the cavity. But if for the
In a way,
experiments,
you're pumping the cavity through this like selection of the.
exactly.
It's like a Maxwell's demon style thing of splitting up the two.
Well, sort of, yeah. So you end up with these atoms in one particular state going in. They are stimulated to emit, and now the maser puts out a signal that is at the frequency that you want. So not only is it a matter in today's atomic clocks, most atomic clocks, you send in a frequency and you keep adjusting it until it makes the atoms make a transition, and that's the way we make atomic clocks today. But this was, in a certain sense, even more wonderful. It would radiate the frequency that you wanted.
It's like once you tuned, you have a.
But how do you then you're tuning your receiver, not instead of tuning the frequency, you're tuning the receiver to know the time.
Well, basically, it's a clock that ticks at the right time without you having to do anything, so to speak.
Yeah.
I mean,
But how do you do it? How do you read it out? You absorb those microwaves.
Well, you got those microwaves. You then say beat those microwaves against some other
I see.
Frequency, and then you get some beat frequency that you can easily measure. Fact is, you could count today. You can count directly 1.4 gigahertz. I'm not sure they could count 1.4 gigahertz directly back in those days. I just don't remember what the technology was like. I was just a boy. But in any case, then what you do is you have something that you want to broadcast, say, to the world. Okay, and you'll use it to compare to what's being radiated by the hydrogen maser, and then by looking at difference frequencies, you can see what the difference frequency is between your oscillator, the hydrogen maser oscillator, and then adjust it so that what's being sent out is some standard frequency that everybody's happy to synchronize their clocks to.
So you tune, you do this sort of like a beat note, like you tune your source to this the hydrogen oscillator, and then you adjust. You kind of know what's the frequency difference.
If the hydrogen hyperfine frequency had been used as a definition of time, and at this time in 1963, we were still keeping time astronomically. Okay, so we were a long way away from this. So basically, it was a way of producing a very stable frequency that you could distribute.
It's just a reference point.
Yeah, so for example, let's say you've got your own laboratory frequency standard. Those days, it would have been a crystal oscillator, and you multiply that crystal oscillator up to something close to the microwave frequency, and then you look at some beat, okay? Then you've got a way of adjusting the frequency of your crystal oscillator. You want to adjust it until that beat frequency is stable. So now you know that your frequency is stable. And now you've got a stable frequency that's as stable as the maser. But the important thing was that this was a way of dealing with the fact that the atoms were going so fast. And
because of all the bouncing around the bottle.
Right. So now they're bouncing around in the bottle. They're not leaving your apparatus. They're staying around for something on the order of a second. It's even better than that. With these atoms moving at over 1,000 meters per second, there's a huge Doppler shift. The Doppler shift is in fractional terms, is the velocity divided by the speed of light. Okay, so the speed of light is about 3 times 10 to the 8 meters per second. So if your velocity is, let's say, just in round numbers, 3 times 10 to the 3,
it's significant.
Then it's a part in 10 to the 5th, and we're talking about making clocks that want to be good to parts in 10 to the 10 or 10 to the 11. So that's a huge problem. But putting the atoms into the bottle, in a sense, solves that problem, because Robert Dicke, back in the 1950s, discovered that if you had anything that was radiating and subject to a Doppler shift, but you confined it to smaller than the wavelength that it was radiating, then the Doppler shift would go away. Or at least part of the spectrum, what was being radiated, would be sharp. It wouldn't be subject to the Doppler shift. So that's exactly the situation you have, because you put these atoms inside a cavity, and the cavity is tuned to the frequency that these atoms are radiating at, and that means that they have to be confined to smaller than the wavelength of the cavity, because the cavity is about the size of half a wavelength. So it's perfect. So they were doing some of the key things that you've got to do if you want to make a real good atomic clock. And we're thinking now, okay, what can we do to make the atomic clocks we have today? This was 1978 that I left.
Was it clear at that point that the temperature of the atoms was the main source, like that was the thing to attack?
Right, because the temperature determines how fast the atoms are going. So if we want to take cesium atoms, which by then had become the thing we used to define time, in 1967, the international community said, we're going to define the hyperfine frequency of cesium to be, 9.19, you look it up. Gigahertz, okay? That's how the second is defined, is that we've defined the hyperfine frequency of cesium. And the problem is cesium atoms are moving not as fast as hydrogen, maybe 100 meters per second, still pretty fast. And all kinds of tricks were used to get rid of the Doppler shift. So it turns out that, if you, uh, uh, well, again, it was a matter of confining the atoms to a small enough distance, putting them in a cavity. The cavity has as much microwave going in one direction as the other, almost. Having a long beam so that you had a long time to observe the atoms. These are the things that people did to get rid of those problems. But those were the things that limited the performance. The performance of atomic clocks in 1978 was limited by the fact that the atoms were moving so fast, be it Doppler shifts, the second order Doppler shift, the relativistic time dilation that Einstein taught us about in 1905, and just the amount of time that you had available. You could think of it as an uncertainty principle. Or the delta T is going to produce a certain delta E, and that's going to affect the line width of the resonance. You just think of it as Fourier transform. I only get to look at it for a certain amount of time. The Fourier transform's going to be broader.
So I'm curious. So at that time, like maybe even earlier, there was like big projects, like before the like Manhattan Project and Apollo Project. So what was the standards for measuring time at those times? Because you're saying that those atomic clocks, they started to appear in the late 60s or maybe closer to 70s. How did people address the time problem before that?
Well, the first atomic clock was made in 1949.
Right.
It took a while before the international community decided they would change the definition of time. In fact, I think they made a really huge mistake in around 1960. So 1949, first atomic clock. It wasn't really an atomic clock. It was a molecular clock. It was an ammonia clock.
What was like the error rate or
Well,
of this clock?
probably part in 10 to the 9, part in 10 to the 10.
Okay.
So pretty good, but nothing like what we've got today. I mean, today we've got parts in 10 to the 19. So, 10 orders of magnitude better than those first clocks. I don't remember what the first ammonia clock was, but soon after that, people did cesium. 1955 was the first cesium clock at the National Physical Laboratory in England. And in 1960, they decided that they would change the definition of the second. Up until 1960, the definition of the second was 1 over 24 times 60 times 60 of the mean solar day. Okay? The trouble is the mean solar day changes. Changes because the tides slow down the rotation of the Earth, all kinds of stuff. Okay? I mean, and it was the mean solar day. It was kind of weird that they didn't use the sidereal day. But the solar day itself changes by 15 minutes over the course of the year because of the tilt of the Earth's axis and the ellipticity of the orbit. So then you have to average that over a whole year. Well, astronomers are good at doing that sort of thing. And until 1960, that was the definition. So in 1960, it had been 5 years since people had been making cesium clocks. And over 10 years since they had made atomic clocks, they decided to redefine the second to be a fraction of the year 1900. Now, in my humble opinion, I think all the people who made this decision are dead now, so this was an idiotic thing to do. They knew how to do astronomy, and they thought, this is great, the year 1900 doesn't change. No, but it's not so easy to measure. Well, they can, extrapolate back, and in 1967, they then redefined in terms of the cesium clock. So people have been making atomic clocks for a long time.
Was this like a huge letdown for the atomic clock people in 1960? Like, did they think that it was finally their year, And
I mean, it's a good question, and I do not know how people were thinking about this, but I did learn the following thing. When they made the redefinition, they decided in order to make a better connection between the old definition of the second based on the mean solar day and the new one based on the tropical year 1900, they averaged what the mean solar day had been for the last, 10 or 20 years. I don't remember how long. But during that time, the mean solar day had been slowing down. So when they made the definition, they were off from the current value of the mean solar day by a significant amount. As a result, when we started to keep time a little bit better, I forget when we actually started to do this, they had to have leap seconds. So what happens is that when atomic time gets out of sync with astronomical time by as much as 9/10 of a second, they put in a leap second so that you never get to be 1 second off. And you've probably heard from time to time, it usually happens on New Year's Eve, that we had a leap second this year. And it's always been a positive leap second. That is, we always get an extra second on New Year's Eve. And
is it for everyone in the world?
Everyone in the world. It's for everyone in the world.
Like some add seconds, some don't.
But not everybody handles it in the same way.
I see.
So some people take that extra second over maybe a period of a day or more, so that nothing,
there's no jumps.
Other people just take it when the international, what's called UTC, Universal Coordinated Time, changes. It's what used to be called, I should say, it's very close to what used to be called Greenwich Mean Time. Okay? So, but now it's based on atomic time with 1 second of offset from atomic time for these leap seconds. Well, the thing is, we've had all these leap seconds because they chose the wrong value for the second. Now, you might say maybe it was a good thing, because we've never had a negative leap second. And nobody knows what might happen if we do have a negative leap second. It's sort of like, remember the Y2K thing?
Yeah.
They didn't know what would happen when we went from 1999 to 2000, because a lot of computer programs only used the last 2 digits. And they didn't know what would happen. Well, it turned out okay, I guess. The world didn't come to an end. But they're not sure what will happen if we have a negative leap second. So maybe it was a good thing, or maybe they would have figured out how to handle negative leap seconds as well as positive leap seconds if they'd done it right. So soon we're going to get rid of leap seconds, just because it's too much of a hassle. And most people won't notice. The astronomers will notice, and they'll be annoyed. But most people won't notice. So anyway, where were we? So in 1978, we're thinking, look, we got to do something about the atomic motion, because it is the main limiting factor in the performance of atomic clocks. At that time, the best atomic clocks were good to about a part in 10 to the 13. And it was a number of things having to do with the motion of the atom. So we thought, not just me and my colleagues, but everybody was thinking, we've got to do something about the motion. And the answer was laser cooling. The idea of laser cooling had been put forth just a few years earlier by Dave Wineland and Hans Dehmelt, and by Ted Hench and Art Shallow separately. The one in the context of ions, the other in the context of neutral atoms. So 1975, the idea. I arrive in 1978. The idea is in the air. People are talking about it. I think, okay, the guys out in Boulder. So we had NBS laboratories out in Boulder. They're working on laser cooling ions. Dave Wineland. Let's work on laser cooling neutral atoms, because after all, the cesium atom, a neutral atom, is the thing that's used as the definition of time. So let's get to work on that. And that's how it got started. I was at a place where precision measurement was important, where best atomic clocks are being developed. And I figured, let me use this background that I have in shooting lasers at atoms to address this problem with atomic clocks. And, we didn't do too badly. My group doesn't make atomic clocks, but people out in Boulder, using techniques that we developed, have made atomic clocks that are better than a part 10 to the 18. Now, one of the things I love to think about is those clocks were good to a part in 10 to the 13 when I arrived at NIST. There was only one clock, I think, that claimed a part in 10 to the 13 accuracy, and that was the clock that were running in Boulder, Colorado. Because of Einstein's general theory of relativity, we know that clocks that are deeper into gravitational potential will run slower. In fact, this was one of the motivations that Dan Klepner had for making such a good clock, to see that effect. Okay, so obviously Washington, where we are now, is a lot lower in the gravitational potential than Boulder. Boulder's at a distance of about 1.5 kilometers, and the shift is about a part in 10 to the 16 per meter. So that means it would be about 1.5 parts in 10 to the 13 difference between Boulder and here. So if I'd had another clock, which I didn't, that was good to a part in 10 to the 13, then the difference between those two clocks was uncertain and about the limit for what the difference in the clock should be due to general relativity. Today, we can see that general relativity difference to millimeters. Isn't that amazing?
Wow. Millimeters in the gravitational field.
Yeah, but if you've got two clocks next to each other, and you move one of them a few millimeters up, you can see the difference.
So how to synchronize the clock? So I assume there's like clocks in different parts of the country of the world.
Yeah. Now, this is not my business, but I know a little bit about it. So depending upon how far apart you are and where you are, there's a number of different things. One of the ways is to be looking at the same satellite that, say, has a clock in it, and then comparing what you see from that satellite, what the satellite is broadcasting compares on the two different places. And in order to do that, you got to take into account the fact that you're going through the atmosphere, and there's an ionosphere, and the way they do that is they have different frequencies broadcasting the time from the satellites. Those different frequencies are affected differently by the atmosphere, and you can work it all out and synchronize the clocks.
Another satellite also carries an oscillator.
Yeah, because the satellite's got atomic clocks in it. It's the GPS satellites are the ones they use. It's called Common View GPS. That's the way of synchronizing. So that's one way. As I said, this isn't my business, so I'm probably not giving a very good description of how it's done. But another way is you send an optical clock signal on a fiber to somebody else. And now you got to be, the fiber has all kinds of things.
Vibration.
Vibration. It stretches and shrinks. So you reflect it back. And you look at how your signal gets messed up by the fiber, two-way trip. And then you subtract that out, half of that, as the signal that the person on the other end should be getting, so you can communicate, and then they can compare what's happening with their clock, and you do it in both directions. And in that way, you can synchronize clocks across, probably hundreds of kilometers. And they're doing this sort of thing routinely in Europe over really long distances. In the U.S., I'm not sure that we're doing it over very long distances. Typically, we're doing it like across town, like in Boulder. The people at NIST will communicate with the people at the University of Colorado using this same idea.
And when you started looking at laser cooling the cesium atoms, what was already what were you building on? So what had already been done?
Well, so we didn't do cesium atoms first because we didn't have the lasers. We only had lasers that could do sodium.
Okay.
So we started with sodium. We figured, you got to start somewhere. And, at the beginning, we were thinking, let's develop the ideas of laser cooling. And then once we've got the ideas developed, then we'll think about how to make the clock. The fact of the matter was, we weren't really thinking ahead that far. We were just thinking, it's going to be cool to laser cool these atoms. And once we got them laser cooled, we'll worry about the rest of the thing. I really think that if we had been foresighted, if we had thought, let's figure the whole thing out, what kind of clocks we're going to make using these laser cooled atoms, we would have given up right at the start. Because the understanding of laser cooling at that time put a certain limit on how cold you could get the atoms. If the atoms had only been that cold, they really wouldn't have made a very good clock. But we didn't worry about that. We just said, hey, it's got to be good. And we accidentally discovered that we can make the atoms hugely colder than what the theory said was possible. In the end, we got cesium atoms 200 times closer to absolute zero than what was predicted by the theory. And if we were stuck with the old, what we now call the Doppler cooling limit, it wouldn't have made a very good clock. But with the cooling limit that we got because of the accidental discovery of sub-Doppler laser cooling, with that, we make damn good clocks. And today, most of the industrialized countries of the world are using cesium clocks to keep time, connecting to the rest of the world through these various means, and basically keeping time for the whole world. So UTC, Universal Coordinated Time, is determined mainly by laser-cooled atomic fountain clocks using the techniques that our research group developed and other research groups developed.
So what made you to contest the Doppler limit?
Well, we didn't contest the Doppler limit. We accidentally discovered that it wasn't right. So here's the story. So when we first finally got laser-cooled atoms down something close to the limit in what we called optical molasses. So the idea is we're bringing laser beams in from different coordinate axes so that we're cooling the atoms along all three spatial dimensions. And Steve Chu was the first to do that at Bell Labs in 1985, measured the temperature. And he developed a technique that we now call release and recapture. The idea is you got the laser beams coming in, cooling the atoms. Now you suddenly turn the laser beams off. Now remember, this is all in a vacuum. So you suddenly turn the laser beams off. So now what's going to happen? Well, those atoms are going to fly apart because they've got whatever thermal velocities they have. They were also using sodium for the same reason we were, that sodium was the only atom that we had the lasers to.
And what were the lasers?
The lasers were dye lasers that we were still
what
using.
Was the wavelength? Or?
Oh, well, the wavelength for sodium, it's the wavelength you see in these beautiful sodium street lamps, 589 nanometers.
Mm-hmm.
So that's a nice sort of orangey yellow.
So you use like sodium kind of based lasers for pumping the sodium? Or?
Yeah, for doing the laser cooling.
I see.
And they were stabilized to about 1 megahertz, maybe a little bit better. That was fine because the line width of the sodium optical transition is about 10 megahertz, so the lasers are well under that. Well, anyway, they measured the temperature by having the atoms just turn off the laser beams. So the atoms are jiggling around, not getting very far because the lasers are damping their motion so strongly. This is where the name molasses comes from, that the atoms feel like they're in a viscous fluid and they can't get out. It takes them a second to get out, whereas it would take them milliseconds to get out if they would just move unimpeded at their really cold temperatures. But instead, they stay around for a long time. And then you turn the laser beams off. Now the atoms, okay, they just expand at whatever velocities they have. And then you just turn laser beams back on after a few milliseconds. And that's the recapture part. So you turn them off. That's the release part. You turn them back on. That's the recapture. And by looking at the ratio of how many atoms are left when you turn it back on to how many atoms you started with, and knowing all the geometry.
How do you count them? Is it fluorescence? Or
we don't count them. We just look at how bright those atoms is by looking at the total fluorescence. And so from that, you can calculate what the temperature is. But you have to know what the geometry is very well. So there's a big uncertainty. So they reported what the temperature was. Now, the theory said the coldest you can get is 240 microkelvin. Now, that's really, really cold, okay? Because room temperature is about 300 Kelvin, okay? And we're talking about getting the temperature down to 240 microkelvin, okay? Dilution refrigerators, sort of the coldest thing that people do when they're doing condensed matter physics. Typically, you get to 10 millikelvin. Okay, if you use adiabatic demagnetization, you can get down to the microkelvins, but it's tough. And here you're supposed to get down to 240 microkelvin. Fantastic. And so Steve Chu measured it with his colleagues, Art Ashkin and John Bjorkholm, whatever. Alex Cable, what a guy. Alex Cable, I'm pretty sure he was on that paper. He was sort of a technician for Steve Chu. At some point, Steve was encouraging him to go to graduate school. He's a really smart guy, really could do all kinds of great stuff in the lab. But he decided instead to form his own company. That's Thor Labs today.
Oh, wow.
Yeah.
That's the famous Thor Labs.
Exactly. That's the famous Thor Labs. So that was started by Steve Chu's technician. He saw all these optical mounts in the lab and said, I can make those a lot cheaper than what we're buying them for. And so he made optical mounts that were cheaper.
So what was before Thor Labs? It's just everyone makes its own components, mounts for...
Well, there must have been other companies. Well, I mean, before Thor Labs, there were companies. I forget the names of some of them, but they were making them. They were just charging twice as much as what Thor Labs charged. And I probably shouldn't be saying this because I got to say, as an employee of the U.S. government, any mention of a private company doesn't mean that I think that they're the best or anything like that. You see, just done for reference. Okay, I have to say that legally.
Yeah, I feel like Thor Labs is like the Amazon of.
Yeah, that's right. That's right. Well, before that, I forget there was other companies. They probably are still in existence, but and they were making these mounts, but they were a lot more expensive. And, make a product that's just as good and costs less. This is the road to success in business.
So it's incredible how this tends to happen in history where people all end up in the same place or like in a very small community. And then like some years later, they're like important all over. There's an amazing thing, which is like there was a year where within a few miles of each other in Vienna lived like Lenin, Hitler, it's like several, the guy who got killed before World War I, like there's just
Trotsky?
Like Trotsky was there, yes, also Trotsky. No, but the guy,
critical mass.
No, the Duke Franz Ferdinand, the guy who was shot when World War I started, they all lived literally. There's a map of Vienna with their houses, and they're like walking distance from each other, in like 1910
but
or whatever.
I'd rather think about a place like Göttingen in 1925. When the people who invented quantum mechanics were all,
or Bell Labs.
or Bell Labs.
I mean, there's infinite examples of this. It's just amazing. Like that, Thor Labs could have been anybody in theory, right?
Yeah.
But in practice, it's like the guy setting up the, optical molasses, right?
And as I understood it, he started that like in his garage.
Yeah.
Maybe his uncle had a machine shop or something, and his business was doubling every year. He was just, the right place, the right time, with the right skills and the right mindset. But anyway, the idea was that group of people made this measurement, and they measured it to be 240 microkelvin, which was what the theory said was the lowest temperature you could get.
I remember in the paper it even says, what is it, plus 200
minus 60.
I have a question. Why is it asymmetrical?
Well, because that happens a lot, that your error bars are asymmetrical because of just the way in which the various contributions to your uncertainty come in. But it's hard to avoid thinking they knew the temperature couldn't be any lower than 240, so they didn't want to put a very very low.
Just nailed it exactly as predicted by Doppler.
So we did the same thing a few years later.
And just kind of, in case someone's listening that doesn't know how this works, laser cooling fundamentally is just you get the atom to absorb. You're putting in a frequency that the atom absorbs only if it's moving towards the laser source, and then when it absorbs that momentum, so it slows down. But then when it emits into a random direction, and therefore net it's slowing down in the direction of its original movement.
Right.
So that's how that worked as well.
That's how what we call Doppler cooling.
Okay.
So
was that the principle behind the optical molasses as well?
Yeah, that's right. But it turns out optical molasses works even better than we had imagined. which we'll come to in a moment.
So there's like a secondary effect that wasn't expected, and that's
right.
where the extra cooling
That's
came
part of the extra cooling, and it makes
So it's not that the Doppler cooling was working better than expected. It's
No.
actually that there's an additional effect
something
that
else
was
going
discovered.
on. That's right, exactly. And right, so we did the same thing, and we were very, very careful. We tuned the lasers so as to produce the lowest possible temperature according to the theory.
Mm-hmm.
And we measured the temperature to be.
What does that mean to tune them? Like, what did you?
Well, so in order to do the process that you described, how do you get the atoms that are moving toward the laser to be absorbing from the laser that they're moving toward, instead of, say, the atoms that are moving away from the laser? If they absorb, they'll speed
They're
up.
going to speed up.
Mhm.
So the way you do that is you make the frequency of the laser lower than the frequency that the atom wants to absorb if it were at rest.
Mm-hmm.
But the atoms are moving. So the Doppler shift, this laser beam is tuned a little bit below the frequency that the atoms would absorb if they're at rest. Then this atom moving toward the laser beam
Sees a slightly higher
Doppler
frequency.
shift sees a higher frequency closer to the frequency it wants to absorb. And so it preferentially absorbs from this one compared to from this one.
Mhm.
And it's that preferential absorption from the laser beams that oppose the motion of the atoms that leads to Doppler cooling. Now, we didn't talk about the heating, but you alluded to the fact that when the atom emits the light, it emits it in random directions. So when you average over that, it doesn't do anything. But it heats the atoms. That is, a random addition of momentum is going to be a heating process. And there's also randomness in the absorption. That is, when the atom is sitting with all these laser beams coming in from all these directions, it's random which laser beam it's going to absorb from. It's not equal probability, because that will depend on the Doppler shift. But there's still an element of randomness, and that element of randomness also adds to the heating. So you balance the heating and the cooling. I can do that derivation in just a few minutes, which I do for students, but I won't do here. And you get the temperature, 240 microkelvin. So we did it in our lab, 240 microkelvin. We did it exactly the same way Steve Chu did it, but we thought we were being even more careful. We tuned the laser to just the right frequency to make the temperature minimum, 240 microkelvin. And then we started to do more experiments because, you got a new thing. Let's do some more experiments. What will happen if we increase the intensity of one of the laser beams? Well, it should push the atoms out. And we could calculate how fast it should push the atoms out. Didn't work. That is, it was much less of an effect than what we had calculated. Change the detuning of the laser. We'd started off with it being optimal, make it bigger. That should make it hotter. Well, we weren't measuring the temperature. We were just measuring how long it took the atoms to get out, because it was so much easier to do that. Measuring the temperature was really, really hard. That was why it's such a big uncertainty. Okay? So we said, let's measure the things that are easy. You've heard the joke about, looking for your keys under where the lamppost is, right? Well, it was a lot easier to measure the how long it took the atoms to get out of the molasses than it was to measure the temperature. So that's what we were measuring. And we calculated what kind of effect that should have. Didn't have that effect. So we were confused. We're doing all these measurements for something we thought we understood, and it wasn't giving the results. So finally, one of my colleagues, Paulette, says, look, we measured the temperature, but we did a slipshod job because it's so hard. What if we really measure the temperature really well? Maybe we'll learn something about what's going on here.
Did anyone else, like other groups, except the Stephen Chu experiment, did other people try to remeasure the temperature?
Not yet, because so hardly anybody working on this. Okay, so this was early days, and people weren't really working on it. I think the group out in Colorado was probably Carl Wyman's group was also measuring with cesium. By this time, we got diode lasers, and diode lasers made it possible to do cesium, and he was getting the Doppler limit for cesium. Okay, so everybody's getting the Doppler limit.
Also, like for Stephen Chu, like his experiment of 1985. So was it like a dead end? So he measured it. All right, everything agrees. That's it.
No.
People
they
tried to.
They were going on.
check?
They were going in a wonderful direction. They were developing laser trapping.
Hmm.
They were making what we now would call an optical tweezer and focusing a laser beam into the molasses
Yeah.
and trapping the atoms. No, they weren't sitting around. Okay. People were doing stuff. They were doing different stuff. So anyway, we decided, let's measure the temperature really well. So we decided the way we would do that is we'd start with the molasses, with all the laser beams coming on, do just like before, turn the laser beams off. So now the atoms expand. And let's put another laser out here. So the atoms will take a certain amount of time to get there.
Mm-hmm.
And when they do, they'll light up and we can measure the time it takes. So if the atoms are really hot, then it'll take less time than if they're going slowly. So we did that. Atoms here, another laser beam up here. We saw nothing. 0 atoms here. And everything was working the way it was, the way it should.
No matter how long you waited.
No matter how long we waited. Well, I mean, after a little while, you don't expect there to be any atoms left. So no matter how long we waited, they weren't there. We checked to make sure everything was working the way it should, pushed the atoms up, to make sure that our detector was working the way it should. Everything's fine. And then we said, what if we put the laser underneath the atoms? Big signal. The atoms were going so slowly, they couldn't make it up. They couldn't get up to where we put the
gravity.
laser. Just gravity.
Wow.
We'd done the calculation. Gravity shouldn't have had any effect at all. At the temperature we thought, the atoms couldn't be any colder than that. So then we put the thing down here. Boom, big signal. And we just measured it, 40 microkelvin. 6 times lower temperature than what was predicted, which was 240. So we were scared. We thought, we're obviously doing something wrong. This can't be true. In fact, I remember months earlier, I had gone to one of the theorists who worked on laser cooling, and I said, look, we're seeing all these strange results. We don't know what's going on. We can't explain it using a 2-level atom. I probably didn't even say that. I said, we can't explain it using any of the techniques that we use. In fact, I had gone the summer before to Paris and spent a month in Paris working with Jean Dalibard and Claude Cohen-Tenuji, trying to figure out if we could determine what was going on. And they were experts at doing things, our effects of high laser intensity coming in, something we couldn't figure anything out. I went to a conference that summer, presented the results, said, people, tell us what's happening. Okay.
This is very rare these days, I guess. You show up at the conference like, look, it doesn't work. Explain, help me.
Yeah, I went to one of the theorists and I said, look, we got all these results we don't understand. If the temperature were a lot lower than what the theory says is possible, maybe some of this might make sense. He said, no, that's not possible. There's no way the temperature could be lower because there's only one characteristic energy in the problem. That's the line width. That's the thing that sets the temperature, and that's it. I said, okay. So then we measured the temperature, and it's 6 times lower. Not like 10% lower. 6 times lower. So we're scared because everybody knows that you can't have a temperature that low. So we decided, okay, we will first check out the thing we were doing. Everything checked out. We found that if we increased the detuning of the laser, made it further from resonance, which is supposed to make the temperature hotter, it made the temperature colder. Then we said, okay, we're doing something wrong. Let's figure out another way of measuring the temperature. And so we went back to the old way.
So did you adjust, so there's like the velocity distribution, so the detuning originally, you would aim for the maximum of this kind of velocity distribution?
No, we wouldn't aim for the maximum velocity distribution. We would aim for the detuning from resonance that would maximize the force. Almost. It's, because of the way the heating and the cooling go together, the place that maximizes the force is not the same as the one that minimizes the temperature, but it's almost the same. So we did that so as to minimize the temperature, which is almost the same as maximizing the force. And it turns out Now we know that isn't the place that minimizes the temperature. That's the place that minimizes the temperature for Doppler cooling, but not for the new kind of cooling that we accidentally discovered.
Mm-hmm.
So what we did was we developed 4 total different methods of measuring the temperature. The old way, what I called release and recapture, except we really took care of all the uncertainties. So in the past, well, we didn't take into account what the shape of the laser beam was, what the shape of the atomic cloud was. This time we did. And we took into account the fact that the atoms were falling, which the old theory didn't take into account because it didn't matter. It was such a small effect given atoms at 240 microkelvin. The fact that gravity just didn't matter. But now we figured we better take it into account. We figured use gravity. Put the thing above, move it down until we start to see atoms. Mm-hmm. See how many atoms that get there as a function of how high it is. And when we had all 4 methods were showing that the temperature was way below the Doppler limit, then we published. And then other people went into their labs and were more careful and found out that, yes, the temperature was lower.
How was the mechanism elucidated?
So when we decided we really knew what we were doing, mm-hmm. we called up our friends in Paris, Jean Dalibard and Claude Cohen-Tanucci, and said, look, we've measured the temperature. We're sure. We measured it lots of different ways. We are positive the temperature is way lower. What's going on? Well, they were so well placed, theoretically, to answer that question. Because they had already figured out a different cooling mechanism that happened when you use really strong laser beams and tune it to the other side of resonance. There was something that would happen that they had dubbed Sisyphus cooling. And now they realized that a similar thing could happen if you tune below resonance the way everybody does at low intensity because of the fact that the atoms were not two-level atoms. You see, the trouble was that all this theory that I've been talking about was based on an underlying assumption that there's one ground state and one excited state. The laser takes you from that single ground state to that single excited state, and it decays back down to that ground state. The fact of the matter is that we were working at the F equals 2 level of the hyperfine manifold of the ground states. There's 5 different magnetic sublevels and a whole bundle upstairs, 7 different sublevels. And we thought we knew that, of course. It's just that we thought it didn't make any difference. Why? Because the only thing that determines the temperature in the Doppler cooling theory is the line width. And the line width is the same for all the different transitions. So we thought, since the line width is the only thing that determines the temperature, it's going to not matter that we've got all these different transitions. Mm-hmm. That was wrong, because it left out all kinds of other wonderful things that happen that we just were ignoring, and that Dalibard and Cohen-Tanucci figured out. And that is, among the things, is that when you put the light on, it shifts the energies of the different states. This is called the light shift. Cohen-Tanucci discovered the light shift for his thesis way back in whatever it was. That's an interesting story as well. This is before lasers.
Could it be somehow related, like, to Stark effects in terms of
it is
in the electromagnetic field?
In fact, today we call it the AC Stark effect. Mm-hmm. So it's very much like the Stark effect. It's applying an electric field, shifts the energy levels. But because there's different strengths of coupling between the ground state and the excited state for the different levels, then you get a different shift for the different levels. But that's not all. When you interfere 2 laser beams that have different polarizations, then the standing wave that's created when you interfere those laser beams will have what we call a polarization gradient. That is, when we sum the 2 fields together and they have different polarizations, they will sum to something whose polarization changes as you move in space, changes over a very tiny distance, a fraction of a wavelength.
Were you aware of that in your experiments when you would send a laser beam? I don't know. Did you put was it a mirror or two?
No, it was all accidental.
Laser?
No, we just used straight mirrors. So we did not change the polarization. But in 3D, you cannot make all the polarizations in the same direction because light is transverse. So if I have two laser beams propagating in this direction, they can be polarized like this, horizontally. And I could have another two laser beams, and they could also be polarized horizontally. When they interfere, it's all going to be horizontal. But now, when I bring in a laser from the other direction, then it can't be in the same direction. It's got to be, or it can be horizontal, but it's got to be in a different direction, because it can't be.
It can't be polarized in its own direction of motion.
Right. So let me do this again. Two laser beams polarized like that. Another two laser beams polarized like that. The one coming down cannot be polarized this way.
Right.
Okay. It has to be polarized like this or like that, and that's going to interfere with the other ones to produce this thing that we call a polarization gradient.
So the fact that the laser beam has a thickness means that they create these like wherever they overlap, there's like a non-zero thickness where there's this polarization gradient.
They're overlapping over everywhere that we want to do the experiment. Right. So it's not like they happen to overlap. That was something that was built into.
It's intentional.
It's like no matter how you try, you're gonna have this polarization gradient.
That's right, exactly. So now we do it deliberately, but back then it was just accidental. And so now what that means is that the different sublevels will be shifted differently by the light in a way that changes as you move through space. So, in a simple case, which Dalibor and Kontinuji figured out, they said, let's imagine there's just two states instead of five, just two states. One, as a function of space, is going to go up and down and up and down, and the other one is going to go down and up and down and up. And it turns out, and there's one other thing, that's optical pumping, also discovered in Paris by Claude Kontinuji's thesis advisor, Alfred Kastler. So it all comes together, you see? Kontinuji had discovered the light shift. Alfred Kastler, his thesis advisor, had discovered optical pumping. And so optical pumping puts the atoms into the bottom of the hill. Now the atom has to climb up the hill, and when it gets to the top of the hill, optical pumping puts it to the bottom of the other hill. And so the atom has to climb again. And when it gets to the top, optical pumping puts it down to the bottom. This is why it's called Sisyphus.
I think we need maybe some brief explanation of the optical pumping.
Okay. So optical pumping is, let's say that you've got a number of different ground states. And those ground states have different amounts of angular momentum. Remember, we talked about the spin of the electron and the spin of the nucleus. Okay, so the spin of the nucleus and the spin of the electron all add together to produce a total angular momentum, and there's two different hyperfine states that have two different total angular momenta, and there are different projections of that angular momentum allowed by quantum mechanics. Okay, now let's say that I shine in light that also has angular momentum. And I start off with the atoms being in all the different states, and I shine in light that has angular momentum. Every time the atom absorbs light, regardless of what state it's in, it goes to the excited state, but because the light has angular momentum, it has to go to an excited state that has more angular momentum than the one it started with. Okay? But when it decays, it can decay back down to the one it came from. It can decay down to one in which it doesn't change the angular momentum. And it can decay back down to one in which it changes the angular momentum by, let's see, you can, that doesn't change, or that it changes it by 1 unit. Okay? So the selection rules is you can change it by either plus or minus 1 or 0. So there's 3 different ways that the atom in the excited state can decay. Unless, of course, it's got the maximum possible angular momentum, In which case, there's only one way that it can decay, which is down to the one that has the one less angular momentum than that, because there's nothing else down there.
Yeah.
Okay, I realize, without drawing it on a blackboard,
Yeah.
it doesn't quite make sense. Yeah, what we need is a blackboard to do this. But the thing is that basically you pump angular momentum into the atom. You start off with the angular momentum everywhere. Some of the atoms have angular momentum pointing this way, some have angular momentum pointing that way, and you shine in light with angular momentum pointing this way. And pretty soon all the atoms have angular momentum pointing this way, because you're pumping angular momentum into it, and you can't get rid of it except by radiating, and there's limits in how much you can radiate away. So you end up with all the atoms in the same place. And it turns out, just by good luck, I guess, that's the lowest, that's the bottom of the hill, the place where the atoms have to pump to. So it's got to climb up, because where else can it go? It's the bottom, so it's got to go up.
When you say it's got to go up, what does that mean? Does it spontaneously cool itself and convert that into the upward movement, or like going up the energy level?
So it's basically it converts its kinetic energy into potential energy in this light shift. Now, where is that potential energy coming from? Well, it's coming from the interaction between the light and the atoms. That is, the light acts on the atoms, as you said, like a Stark shift, and changes the energy of the atoms. And that's what creates the potential energy that makes the atom climb up the hill.
So what creates this, the modulation, what we're talking about? So there is I guess, several things. One is change in polarization gradient. So it kind of varies from one spot to another one. And then also intensity, right? Because you have two counterpropagating beams. This is maybe on a larger scale.
Okay, but you're right. In the simplest case, if I have two laser beams with the same polarization that are counterpropagating, then there's going to be a change in intensity and no change in polarization. But if I have one of them with a polarization like this and the other with a polarization like that is orthogonal linear polarizations, then there will be no change in intensity.
I see.
But only a change in polarization. In general, there's everything. Polarization changes, intensity changes, but it all works out that this process of polarization gradient or Sisyphus cooling works out, and the atoms get way, way colder than what they should. So once we realized what was going on,
just a question, in the end, where does the energy go when they get colder? Okay. Is it being radiated away? Where can it go?
Now, that's an important point. And there's only one place it can go, and that's just what you said. It radiates away. In the end, the scattered photons have more energy than the incoming photons. And in fact, we used that feature as a way of learning about what the atoms are doing, because
doesn't this almost imply like a source of energy?
No.
Like, let's say you could scale this up, by 10 to the whatever, like with an enormous amount of atoms. Could you? Is that a power plant? Like, are you outputting? Can you put a solar panel on the other side? And,
it's
a photovoltaic array and start, generating more electricity.
It's one of the worst power sinks you can imagine. I mean, as you well know, you're not going to beat the second law of thermodynamics.
Yeah.
You're not going to extract energy from the thermal motion of the atoms. Cooling them down and extracting that energy and get to use it. That's just not the way refrigerators work. If that was true, then we could just plug in our things to your refrigerator,
and it would get cold and power your house at the same time.
That doesn't happen. What happens instead is you generate heat, and that heat has to be taken away.
Are the losses then mainly in the fact that these lasers are mostly doing nothing? Like, most of the photons are just passing through, so those are all wasted.
Well, most of it has to do with the fact that I got to plug the laser in.
Right. The laser has to be powered.
And I get maybe in the old days, less than a percent of the power that goes into the
laser is actually coming out as photons.
Actually goes into the light from the laser, and then that has to be used to pump another laser. And that's inefficient. I mean, today it's a lot better because we're using diode lasers, which are a lot more efficient. But still, there's a lack of efficiency there. But the amount of energy that is involved in taking
these transitions are very small.
So tiny In fact, one of the things that I like to point out is if you were to take all of the atoms that have ever been laser cooled in all of the laboratories over the entire world, and then take those atoms and compress them into, it would hardly make a speck of material. Because the typical kind of thing that we create is atoms, maybe, if we're lucky, we might have 10 to the 8th, 10 to the 9, sometimes 10 to the 10 atoms that we start with. And we could create those atoms every few seconds, 10 to the 10. Think about what a mole is. A mole is 10 to the 23. Okay? So even if every second you're making 10 to the 10, and there are 10 to the 7, 3 times 10 to the 7 seconds in a year, and you did it continually.
You'd be lucky to get
now you're talking about 10 to the 17, okay? And there's 100 labs over the world, right? So that's what? 10 to the 19. I'm just, trying to do this very back of the envelope. This is still a long way from a few grams. This is still a fraction of a gram of sodium.
Is there, okay, this is just this is definitely not a good question, but just once you have these atoms and they're trapped and cooled to these extremely low temperatures, is there some way to, if these were, let's say, well, actually, it doesn't even matter which atom, they're light atoms. Is there a way to, for some reason, fuse them? Like, does this somehow enable fusion? If they're extreme. I'm just curious. Yeah. Like, is there some kind of wraparound effect where, like, either they have to be extremely hot or extremely cold, and then they can pair up?
Okay, now as far as fusion, I mean, if you're talking about fusing the nuclei, no, absolutely not. It was funny because
did you guys think about this? Like, did you consider maybe we're going to? I mean, maybe there's an effect, right? There's a lot of surprising things happening.
So what was going on was about the time that we did this was about the time that cold fusion was a thing. And so we were getting these crazy people who would say, well, you got these atoms really, really cold. Maybe it's going to make cold fusion work. And first of all, I would say, well,
my intellectual ancestors here.
Cold fusion doesn't work better because things are cold. It just works in spite of things being cold. And then the other thing is it doesn't work at all. So that was kind of funny.
You're skeptical, it sounds
like.
But
yeah, I mean, cold fusion. I think the whole cold fusion. Yeah, I think the whole cold fusion thing is a great example of the way science is supposed to work. Somebody comes up with some result that seems too good to be true, and then a whole bunch of people try to replicate it and fail.
Yeah,
and then they figure out what went wrong with the original person's thing, and I think now we have a pretty good idea what went wrong with those original things, and that's the way things are supposed to work. Now, there are still some crazy people who think that cold fusion works, but it doesn't. And I think it's been proven very effectively that it doesn't work, and that's just the way science ought to work. Sure, there's going to be some spurious results sometime because people forgot about this or that when they did the experiments and didn't check enough. That's why
this is what you were worried about, right?
We spent months before we published to make sure we weren't making some stupid mistake.
So what went wrong with the Stephen Chu's experiments? Was it just the error box, or did something went wrong?
Okay, so that's a really interesting question. We already know what went wrong with our experiment, where we first got 240 microkelvin, because we deliberately tuned the laser to the place that the old theory said should produce the lowest temperature. That's what went wrong with our thing. And then we stopped measuring the temperature because it was too hard. In Steve Chu's case, he had an ion pump near where the experiment was going on to keep the vacuum good. And the ion pumps always have a little magnet on them to help the pumping process, because you want the charged particles to follow spiral paths so that they can ionize more atoms. That's how an ion pump works, okay? And the magnet was producing a field of on the order of 10 to the minus 4 Tesla, that is a Gauss, something on the order of the Earth's magnetic field at the position of the atoms. Well, the atoms, the line width of the transition is 10 megahertz. A Gauss field is going to shift the frequency of the states by a megahertz. It's just not going to make any difference. So he didn't worry about it. For some reason, we did. We decided when we built the apparatus, let's make sure that the field where the atoms is really small, just in case. Who knows? Let's just make it really small. So we adjusted it so it was about 10 milligauss, probably 100 times lower. Well, it turns out that if you put a magnetic field on, it shifts these energy levels that have been shifted by the light shift in ways that you don't want, and basically destroys the process. And we learned that. Once we knew what was going on, we said, okay, let's deliberately apply a magnetic field and see what happens. And we found that if you apply a magnetic field of 1 Gauss, then you get a high temperature. So that was what was going on. We were just, again, it was just luck. We had no good reason for making the field really low. We just thought, it's not going to hurt anything. We can always apply a field later if we want to. Let's just make the field low. And we got lucky.
So once you got that way below the Doppler limit, did you aim pushing further the boundary?
Sure. So as soon as we knew how it was working, then it was clear, what do you do to make the temperature lower? And 2 things. You tune further from resonance and you reduce the intensity. This sounds crazy. Making the intensity of the laser lower is going to make it colder. Because, of course, the laser is what's doing the job. But it turns out, up to a certain point, there is a limit. You can't, obviously you can't turn the laser off. So there's a limit to how low you can turn the laser. And basically what it is when the amount of energy that is taken out of the atom's kinetic energy by climbing up the hill, when that energy is comparable to the amount of energy that the atom gains by radiating a photon, because there's a recoil, okay, then you're done. You can't do any better than that. So you can't turn the laser down too much, because that'll lower the amount of energy removed by the Sisyphus effect, so that it's below the recoil energy, what we call the recoil energy.
So now instead of level width, which is Doppler limit, you went to the recoil.
Almost to the recoil limit, yeah. So the recoil becomes the new limit. It was a few times the recoil limit. It was
and recoil, just to explain, this is the spontaneous emission of the photon once.
Right. Well, it doesn't have to be spontaneous. It's also the energy gained when you absorb a photon. Basically, it's the kinetic energy the atom picks up if it started at rest and it either emitted or absorbed a single photon. That's what we call the recoil energy. And this process of laser cooling, what we now call polarization gradient or Sisyphus cooling, gets you down to several times the recoil.
And what is that if you put it in numbers?
So for sodium, the lowest we were able to get was, I think, 25 microkelvin. I think the recoil limit's about 3 microkelvin. For cesium, we got down to 0.7 microkelvin, and the recoil limit is, if I'm remembering correctly, 0.2 microkelvin. So
what is the reason for this? Is it just that bigger atoms are heavier, so their speeds are slower?
That's one of the big things. Cesium being heavier means that its recoil energy is smaller, plus the frequency of the laser.
Is it that the recoil energy is the same, but the temperature is lower because the speed is slower, or is it like the joules are different, or is it
it's actually the energy is actually lower.
Okay.
So, and for 2 reasons. One is that the frequency, the laser frequency required to excite cesium, is lower than what's required to excite sodium, and it's heavier. The energy is equal to, not surprisingly, p squared over 2m. It's the kinetic energy. And p is the momentum of the photon, which is proportional to its frequency. Okay? So the energy is 1/2 h bar squared k squared. K is the what's called the wave vector, 2 pi over the wavelength. So it's 1/2 k squared h bar squared k squared over 2m. M is bigger, K is smaller. That's what makes the recoil energy smaller. And there's another effect that comes in, which again we discovered accidentally. We we were very careful when we were measuring the temperatures of these things to say we measured the temperature of atoms released from optical molasses. Now, if we had the atoms in the optical molasses, we turn it off and measure the temperature. We were very careful to never say that we were measuring the temperature of the atoms in the optical molasses, because we figured we don't know what happens when we turn it off. Turns out something very good happens when we turn it off. With all these laser beams coming in and interfering with each other, it makes a kind of a what we call now an optical lattice, because there is a change in the intensity, as well as a change in the polarization that affects it as well. You make what sort of a three-dimensional egg carton for the atoms. They like to be in the places where the energy is lowest. And the laser cooling works so well that the atoms actually get trapped. In fact, a lot of our work since then has been in studying the atoms moving in optical lattices. But what happens is, if you turn the laser beams off slowly enough, then you do an adiabatic cooling of the atoms. You got to have the right time scale to turn it off. Get adiabatic cooling, just like, if you take any gas and expand it, it'll get colder. If we expand the optical lattice, that is by lowering the depth of the lattice, then it will make the atoms colder. And that was happening as well. And that's how we got down to 0.7. But again, it was sort of by accident. We learned that we got better cooling. The first way in which we would turn the laser beams on and off was we would shine the laser beams through a mechanical chopper. So this is a piece of metal attached to a motor that's going really fast. And we would cut slots and holes. And so when the thing came around, it would let the laser beam through. Well, that's not nearly as fast as the electronic ways that we turn laser beams on and off now, using things like acousto-optic modulators. But we didn't have acousto-optic modulators when we first started, so we used these mechanical things, and they were slower. So they would turn off the laser beam on just the right time scale to maximize this adiabatic cooling. And so we got even colder temperatures. And now that's done deliberately.
What do you think is like how do you expose yourself to luck? What's the right way? How do you what do you think is the is there wisdom about that you've come to?
Well, people have said all kinds of aphorisms about this, that luck favors the prepared mind.
Do you agree with that?
Well, sure,
in your
of course.
experience?
Of course. I mean, if you don't know enough to recognize that something good happened, then obviously you're gonna pass it over. Steve Chu said, if you had to choose between being lucky and being smart, choose lucky. Now, that's easy for him to say because he's really smart. But so obviously he believed in the power of luck a lot.
Do you think the opposite argument would be that things like this are happening all the time, but usually people just ignore them? That would be that would mean that it's not lucky at all, in a way.
I don't know.
It's kind of like what's an example of this? Yeah, if no one's looking, there might be many things happening, but if no one's looking, then it feels lucky if somebody goes outside and sees a shooting star or whatever.
Yeah, I don't.
But if you're not looking, there's shooting stars all day.
I don't know. I'm sure there are things that happen that people ignore, but I don't think they're happening all the time.
Mm-hmm.
I think that people who are doing research are tuned to be looking for something. They've heard too many stories about, look, somebody said, and I think this is really so true, the way science advances is not eureka. The way science advances is, oh, that's odd.
Yeah. For sure.
And, people have heard those kinds of dictums over the years. So I think that they're prepared. But here's another thing that both Steve and we shared. He discovered something he called it super molasses. It was where you would have the laser beam shining in and looking at how long it took the atoms to get out. And when the laser beams were cranked up really high in intensity, higher than what we would normally do to get low temperatures, and also tuned fairly close to resonance, which is also what we would not do to get cold temperatures, then the atoms would stay in the molasses a lot longer, and the density of the atoms would be a lot higher. And this sounded wonderful, except for the fact that the temperature was pretty high, so that wasn't so good. And he tried to figure out what was going on, and we tried to figure out what was going on. And Mar Prentice, who was at Bell Labs at the time, he was at Stanford by now, tried to figure out what was going on. None of us ever figured out what was going on. I think Mara had some good ideas. She's at Harvard now, but we all gave up. And I think it was the right thing to do because there was other stuff that was more interesting and, that we could learn a lot about and that produced really good new research directions. But it's still an open question as far as I know. What was going on? What's the detailed explanation? We guessed, maybe some kind of trapping is going on, but we couldn't figure out how the traps were being formed. So it's not a solved problem. And, maybe we overlooked something really important.
Mm-hmm.
Somebody will come along and decide, how about if I try this? Maybe this will explain it. And it turns out to be something really wonderful. We don't know.
Did your work get quickly adopted? Like once you had these extremely cold atoms, was that quickly converted into a clock or what happened?
Yes. Well, it was converted into a clock within, a few years, I guess. Yeah.
Mm.
So once we got cesium down to 0.7 microkelvin, this was pretty clear you were going to have to make a clock. And we started to think about, in fact, we even made some prototype clock apparatus, but the real clock people in Boulder who make clocks, they took these ideas and refined them and now what are called atomic fountains. So this is an important thing. So you may have heard the term atomic fountains these are what make clocks. So what they do is you cool down the cesium atoms to below a microkelvin. You then toss them up in the vacuum, of course, and they come back down after about a second. You toss them up a meter, comes back down after about a second.
Why does it come back down?
Gravity.
Gravity.
It's just gravity. You let go of anything and it falls. Right. You toss it up, it'll...
What does it mean to toss it up? Like what gives it the impulse to go?
Well, that was something that we worked out and other people worked it out too. So think about this. You've got these laser beams coming in from all directions. And the atoms, the only thing the atoms are seeing is the laser beams. They're not looking at the rest of the lab, right? They can't see anything but the laser beams. How do they know to cool down to a temperature close to zero velocity? They've got a distribution of velocities centered around zero. How do they know what zero is? Zero velocity is when all the laser beams have the same frequency because the Doppler shift is zero. So what we do is we fool them. We take the lower laser beam and increase its frequency. The upper laser beam, the one coming down, decrease its frequency. Now the atoms think that the zero velocity is when they're moving up. So we just, after getting them cold and we shift the frequency, then they cool down again to something that's moving up. And then we turn everything off and the atoms go up, they come back down. And that coming up and going back down gives you a whole second of observation time instead of the milliseconds of observation time that you got with the old atomic beams, which had 100 meters per second and a meter length or something like that gives you 10 milliseconds. So instead you get a whole second. So you get 100 times narrower line.
So if gravity is 9.8 meters per second squared, are they going roughly like 5 meters per second when you let go of them? And so that takes about half a second?
Yeah, it's more like 2
or whatever it is.
Whatever it is. It's a freshman physics calculation.
But it's literally that. That's kind of my question is like, it's literally what's happening.
Literally that. That's right.
That's fine. Okay.
And so...
isn't it kind of a happy accident that you don't need to build like a column, like a 100-meter column for this or whatever? Of course, they're going so slow.
Of course, you would love to have more than a second.
Right.
The trouble is that the height goes like the square of the time.
Mm-hmm.
So if I want 10 seconds, I do need 100 meters.
Right.
And so people are making those things. In fact, this is, another wonderful story. The coldest temperatures that people have gotten, doing some other tricks, basically adiabatic expansion, but using a trick that we call delta kick cooling that makes it behave like adiabatic expansion, but a whole lot faster. The coldest temperature have been done in a drop tower. So they've got this tower in Germany, in Bremen, I think, and it allows several seconds of drops. So you build a whole apparatus and you drop it from the top of the tower. And you laser cool the atoms and you make a Bose-Einstein condensate. We haven't even talked about that. And then you let it expand and cool it down to, I think, 30-some picokelvin. That's the record. Wow. And it's in this drop tower. The space station doesn't do quite as well, almost, but not quite as well in the space station. Space station, things aren't falling, so you got longer time.
Mm.
So, that's good. And there's now some atomic clocks in the space station. They're working beautifully. The fact that they don't fall allows those clocks to work even better. But on Earth, we have these atomic fountains. They toss the atoms up. They come back down after a second. They pass through a microwave cavity on the way up. They pass through the same microwave cavity on the way down. That's the beauty. It cancels out all kinds of bad things.
Is it the most adopted architecture right now for atomic clocks?
For cesium atomic clocks.
Cesium atomic.
Which is the definition. It's the thing. If you want to be contributing to UTC, then even that's not entirely true, because people have measured the ratio of cesium to some optical frequency standards, and they can contribute to UTC now as well. But if you want to really be official, you do cesium. And so in national metrology institutes all over the world, people have laser-cooled cesium fountains, and they're good to a few parts into the 16.
So what makes cesium that favorable?
Right. Why cesium?
Other atoms?
Well, remember, it was decided in 1967. So it was before laser cooling and really before there were decent lasers. So why cesium? Okay, a number of reasons. One is so heavy. And for reasons that I don't understand, but I'm sure some condensed matter physicists understand it very well, you don't have to heat it up very much to get a decent vapor pressure. So it's a solid at room temperature, but it melts, not very hot, and you get a decent vapor pressure. So that means heavy and not very hot, the atoms are going slow. So that's good, because we don't want the atoms to go
when
fast.
you evaporate them, they will already... you don't have to heat them up.
Don't have to heat them very much.
Cesium is like a soft metal, right?
Soft metal,
it doesn't have a strong crystal lattice.
Yeah, but gold is a soft metal, and it has a very high vapor pressure. So that's not the whole story.
That's a good point.
And I'm sure people understand this, but I don't. It's one of those things. I would love somebody to explain why cesium has such a high vapor pressure and gold doesn't. But
I think being okay, I can maybe explain this. This is not fact checked, but probably gold is malleable.
It is malleable.
It has a strong lattice. It's probably more about like the defects and things like that. I think cesium and lithium and these like first, column periodic table metals just don't stick to themselves that much.
Pure gold
Something
is quite
like that.
soft.
Yeah.
You can bite it.
Yeah, but that might be more about the defects, like the crystal structure can slide over itself.
That might be. I mean, it's
rather than like that you can tear it apart.
Could be. Yeah, it's obviously both of these things are polycrystal. We're not not talking about single crystals of any of these. So I don't know.
Yeah, that's true. The softness is actually probably just, I brought that up, and that's probably just irrelevant. That's actually like the...
I don't know. I mean, obviously there's something having to do with what the...
just the bond strength between
it relates to the heat of vaporization and things like that, I guess. Well, anyway, so that means the cesium atoms that you make the atomic beam out of are going fairly slowly compared to if you did this with, say, hydrogen, which would be, a disaster. Plus, of all the alkalis that are not strongly radioactive, I say strongly because rubidium's a little bit radioactive. Not much. It's got a lifetime of the age of the universe. It's got the highest hyperfine frequency. As you make the atoms heavier, you get a bigger hyperfine frequency. It's probably just a matter of the wave function having higher density of atoms.
I think I've just generated another stupid question. So why don't we just use radiation as a clock? Why do we need this? Seems all very complicated. Why not just use a Geiger counter and watch, the decay? Because that's also should be quite predictable, right?
Okay, well, if you could imagine using the rate of radioactive decay would be a bad clock, because for one thing, it's stochastic.
Mm-hmm.
So the rate at which I get counts is random.
But what if you have a very big chunk of?
Sure, but that means it's only going to get better, like the square root of the number.
Right, I see. So you need an enormous chunk of
and
material.
Okay. I mean, you wouldn't be able to lock a single frequency to it and then distribute it, because it's still random.
Yeah. Okay.
Now
you could measure over a long time, right? Like if you were going to do like a day, right? You would get a lot of counts over a day.
But it's so much easier to do it than when we are doing it.
Now that we have the atomic clocks, yes.
But you aren't too far from something that's really interesting, and that is we're now thinking about using nuclear energy levels as the clock frequency. So now, we started off talking about hyperfine. That's orientation of the spins.
Yeah.
Today, we're talking about, we haven't talked about, but today we're going to move to optical frequency standards. These are actually electronic excitations. So putting the electron in a different orbit, and that's going to produce optical frequency. So instead of being microwave at the order of 10 to the 10 hertz, we're going to be talking about optical, which is a few times 10 to the 14 or 10 to the 15 hertz. That's what the new clocks are going to be. But nuclear transitions are even higher. I didn't really quite get to the thing, why do I want the higher frequency? Because if there's anything messing up the performance of the clock, let's say a little magnetic field, shifts things a little bit, I want that to be a smaller fraction of the clock frequency. So I want a highest possible clock frequency.
Just having something high energy protected from noise sources that are...
Well, it's not so much that it's protected.
Well, it's just less, the contribution
is
smaller.
Fractionally less of a problem. So... So anyway,
how do you affect the nuclear energies? Like, how does that even work?
You do it with a laser.
Okay.
But only just like recently, like in the last few months, they've done it with a laser. They've excited a nuclear transition with a laser.
Also, aren't we not limited by the width of the sources which pump the laser, which pump the atoms? Like,
yes, for example. And there's only one transition that's any good in thorium. There's a gamma ray. And I say gamma ray not because it's such high energy, but because it's a nuclear transition. So there's two isomers of thorium. One of them is a few electron volts above the ground state. So that produces a photon that is higher than these optical photons, right? It's in the ultraviolet. I don't know whether it's called extreme ultraviolet, but anyway, it's low enough that you can multiply a visible laser up and use the harmonic of the visible laser to excite the nucleus. And they've just done that a few months ago. And everybody's excited about it, but it's so far in the future. We got so many problems we're going to have to solve for that we're not even thinking about it as a candidate for the next definition of the thing. The next one after that, maybe.
Did you run into, or do people run into, I mean, now, kind of this whole clock business has turned into atomic quantum computing, right? So in a way, it evolved into that, like a side branch. Did you guys run into quantum effects that you actually had to get rid of, or how come this roughly the same apparatus can be used as a quantum computer and a clock?
Yeah.
And can you just ignore the quantum effects in the clock, or how does that work? Like the quantum entanglement between the atoms and things.
Yeah, well, you can't ignore the quantum effects because it was quantum mechanics that let you do any of it in the first place. The thing is so fundamentally quantum mechanical right from the start. I mean, the fact that atoms have energy levels is a quantum mechanical feature. I don't know if you can see it, but I'm wearing a tie that has a picture of an atom on it.
Orbitals.
Now, when I say a picture of an atom, what I mean is, if someone was to ask you, draw me a picture of an atom, this is what you would draw.
Thing you might
right? This is the Bohr-Sommerfeld-Rutherford atom, right? Totally wrong, right? I mean, this is a completely wrong picture of an atom. It shows electrons, following orbits going around. That's so wrong. the electron is in some kind of a wave function that surrounds the atom. It's not at some point and going around. And that, of course, is what we're celebrating this year, the 100th anniversary of finding out that you can't treat an atom this way, that you've got to treat an atom in a completely different way. That's what Heisenberg discovered. Schrodinger discovered a different way of thinking about it a year later and then proved that they were the same as what Heisenberg had discovered, that this idea of an orbit is just dead wrong. But it was the beginning of our quantum understanding of the way that
It's just like the
that atoms
intuition
work.
from the planetaries orbit.
Yeah, that's right. It was very much influenced, I think, by our understanding of the planetary model of the solar system. You think, well, the atoms must be doing the same thing. Once Rutherford understood that atoms were not a plum pudding the way Thomson thought, then there's all these things that came together early in the 20th century. So it's not like we're trying to avoid quantum mechanics. In a sense, quantum mechanics provides
It's where the whole that's where the gears of the clock come from.
But
way, right?
By being able to do laser cooling, we can push ourselves to the quantum limits. And only when you push yourself to the quantum limits can you do things like quantum computing. So, for example, I need, if I'm going to use neutral atoms as qubits in a quantum computer, I have to know what the state of my atoms is. I can't have my atoms distributed over a whole bunch of different motional states. I better know to, as well as quantum mechanics allows me to know, where it is and what state it is. And only by laser cooling have we been able to do that for atoms, say, held in optical traps. The way, have you talked to Misha Lukin?
Yes, we did.
So he holds these atoms in optical tweezers. The thing that I was saying Steve Chu was doing next after he got the optical glasses, whereas we were doing like magnetic traps, and both things are important, right? And then we haven't even talked about the magneto-optical trap. Jean Dalibard, the one who explained, along with Claude Cohen-Tanucci, what was going on with the sub-Doppler cooling, invented the trap that everybody uses, the thing that revolutionized laser cooling, called the magneto-optical trap. And it's just magical. It gets atoms dense, cold, ready to go to the next step, where you cool them a little bit more using the polarization gradient techniques that we have, and then put it into a magnetic trap. And we haven't talked about magnetic traps, but our group was the first one to do magnetic traps. Wasn't a very good magnetic trap, but it was a start. And now you put it into good magnetic traps and you do evaporative cooling.
How does the magneto-optical trap work?
It's wonderful. So you bring in laser beams from all directions, just like with optical glasses. But now you choose a particular set of polarizations. The laser beam coming in this direction is circularly polarized. I don't remember. Well, it depends on where the magnetic field is. They say polarized that way. The one going the opposite direction is circularly polarized the other way. Each of the pairs have pairs of opposite circular polarization. Then you put a magnetic field on. And the magnetic field is produced by what's called a quadrupole, which is what we used for our first magnetic trap. The one that I said wasn't so good, but it works beautifully here. So you put this magnetic field on, and the field is zero at the center, and it increases linearly as you move away from the center. So the quadrupole is two loops of wire, but with a current going in opposite directions. So obviously, on axis in the middle, the field has to be zero because it cancels out. But then you got these lines of magnetic field that are going like this and diverging as they come away from the coils. And so the magnetic field changes linearly. That is, it increases linearly as you move away from the center. So there's a Zeeman shift that increases linearly as you move away from the center. There's a Doppler shift that increases linearly as you change the velocity from zero. The whole thing works together. It takes a few lines on a blackboard to prove this, such that there is a force on the atom, the Doppler cooled force that we've already talked about. It's linear in the velocity because the Doppler shift is linear in velocity. And there's a restoring force, again, because of an imbalance between the force of the two laser beams that's linear in the position because of the Zeeman shift, shifting you closer to resonance with the right laser beam. So there's two things going on at once: a force that goes against the velocity, that's linear in the velocity, a force that goes against the position that's linear in the position. This is what you study as a freshman in physics. It's a damped harmonic oscillator, right? You've got a force, a restoring force, that's the spring, that's linear, pushing you back toward the center, and you have a force that is linear in the velocity, that's putting the mass in an oil bath or something, right? Okay? This is what Dalibard figured out for the atoms. So you just pour atoms into this trap, and they stay. If it was a magnetic trap, you pour atoms in, and they go right back out again because there's nothing to damp their motion. Here, you pour the atoms in, and they stay. Put this on the end of a Zeeman slower, and you're just pouring atoms in. So you get this huge number of atoms, and then you transfer them to a magnetic trap where you don't have any lasers scattering, and that way there's no more heating. You cool them down by evaporative cooling, something invented in Kleppner's laboratory for doing Bose condensation, which they were trying to do. So coming back to Dan Kleppner, he came to me in 1976 and said, I just read this article where this guy said, you might be able to make a Bose-Einstein condensate out of a gas of hydrogen atoms. I'd like to try it. Would you like to work on this? And I said, you bet.
Well, it's like the holy grail, probably. At that.
Yeah. And I worked on it for 2 years, didn't make much progress. 20 years later, they succeeded in getting it, and never did anything decent with it. But in the process of getting it, created the tools that allowed other people, like Eric Cornell and Carl Wyman and Wolfgang Ketterle, to do it with rubidium and with sodium. That is, Dan Kleppner and his group developed the tools, the evaporative cooling, the magnetic trapping, that allowed them to the other people to do magnetic to do Bose-Einstein.
So evaporative cooling was already
it was in Dan Kleppner's, right?
That time.
Right.
Wow.
How does evaporative cooling work? I mean, it kind of suggests
Just
the name. The name.
Your
suggests.
coffee is too hot. You blow on it. What's happening when you blow on the coffee? You're getting the humid
Right.
saturated air moved away, so more water can evaporate, and every water molecule that evaporates takes away more than the average energy of the water molecules that are in the coffee, and so the coffee cools down. You arrange to lose atoms from the trap.
And you just lose the high energy atoms, basically.
You arrange to lose the high energy atoms. That's part of it. The other part is what's left has to re-equilibrate and produce a new Maxwell-Boltzmann distribution of velocities. So there is another set of high energy atoms, and you can get rid of those. If the atoms don't collide and re-equilibrate, this doesn't work.
How do you lose them? What does that mean? You have like an edge. You tune it to where it's just barely trapped, or
you tune it so that the highest velocity atoms are just barely trapped, and then you let them escape.
Right.
That's one way. There's another way. You tune it so the fastest atoms are going to get to the highest value of the magnetic field, and when they get there, you use radio frequency to flip their spin energy. That's called forced evaporation.
That's basically like a spatial thing. So you're separating them spatially, and then there you're kind of knocking them out.
Yeah.
Okay, interesting.
Yeah. I mean, it amounts to the same thing. The highest energy atoms get to the place where they see the field that
they're
flips
at the edge
their spin.
of the.
Alternately, they just get to the edge of the trap and spill out.
Got it.
And only the ones that are going to the highest velocity spill out. So, this has all worked together: the laser cooling, the trapping.
But this evaporative cooling doesn't really work well unless you first laser cool it, because I guess you just lose all the edge. They're too chaotic. Or
you just wouldn't be cold enough to
use the trap.
Started, yeah.
Right. Okay.
I mean, you really have to be pretty cold before you can before you can get atoms in any kind of a trap. Neutral atoms are very hard to trap.
Right.
And before laser cooling, basically there were no traps for neutral atoms. So once having done optical molasses, Steve Chu and his colleagues do laser trapping. Once we got laser cooled atoms, we did magnetic trapping. And the combination of those two things is used routinely all the time to make Bose-Einstein condensates.
So what's your retrospective now on this Bose-Einstein condensate experimental demonstration? So you said the ideas of implementing, like showing it experimentally, was back in 70s, and then to showing in 90s. So it was like
Yeah. Okay.
20,
So
maybe more years.
So it even goes back further than that. Einstein figured it out in 1924,
Yep.
based on the idea that Bose had about Bose invented quantum statistics. So based on the new idea of quantum statistics that Bose invented, Einstein figures out what we call Bose-Einstein condensation. A lot of people think Bose worked with Einstein on it. No, Bose came up with the idea of quantum statistics. Einstein took that idea and calculated Bose-Einstein condensate.
I think it would be good to explain also what is Bose-Einstein condensate.
Okay.
Like just a little
So
bit.
if you have a gas of atoms of a certain sort, namely bosons. Now, there's only two sorts of things in the world, bosons and fermions. That is, when we go to the level of atoms and subatomic particles, everything gets classified into one of two categories, bosons and fermions. And the difference is that bosons love to be together and fermions are forbidden to be together. To be more explicit about it, it is impossible to have two particles that are the same kind, that fall into the fermion category, electrons, for example. It's impossible to have two electrons in the same quantum state. This is what leads to the Pauli exclusion principle and having chemistry and all that. But there's another class, photons are one example, that are bosons. They love to be in the same quantum state. That's why we have lasers. A whole bunch of photons in the same state. But there are certain atoms, like sodium, rubidium, that are bosons. And they love to be in the same state. And what Einstein figured out in 1924 is that if you get a gas of such atoms, cold enough and dense enough, then a phase transition happens. It's a phase transition from one kind of a gas into another kind of a gas. Start with an ordinary gas where there's all kinds of different velocities. And then you get it cold enough and dense enough, and suddenly a whole bunch of the atoms go into the lowest possible state, which Einstein thought was stopped. That was before the Heisenberg uncertainty principle, which was 1927. And so the Heisenberg uncertainty principle says, well, they don't stop. They just go into the lowest possible quantum state available. And that's Bose-Einstein condensation. So all of a sudden, you have a huge fraction of the atoms in the lowest possible quantum state, as if it were a gas at absolute zero. But it's not, because there's a few atoms that are hanging around that are not in the lowest possible state. But this is amazing, because almost for free, you get something that's almost a gas at zero temperature. And then do all kinds of wonderful things. But then you asked another question.
In terms of the history of experimental demonstration.
Yeah, so then 1976, two guys, Lou Nazanov and Bill Stwally, suggest you could do this with atomic hydrogen. Because, remember the thing about forming molecules? If you make the gas dense enough, then you're going to make molecules by three-body collisions. But what they said was, if you make all the spins of the electrons of the hydrogen atom point in the same direction, then they cannot form molecules. The two hydrogen molecules where the electron spins in the same direction have no bound state. So that sounded wonderful. So Dan Klepner goes to Tom Graytak and says, does this make any sense, this Bose-Einstein condensation, which I never heard of before? And he says, this is wonderful. And so they say, let's do it. And they come to me and say, would you start this up? So I did. I'm a postdoc now. As I said, didn't get very far. We just, but what happened in that lab after I was gone enabled Bose-Condensation to happen in 1995. I think it was 1998 that they finally did it with hydrogen. And hydrogen was just a long atom because it just didn't have enough collisions to re-equilibrate before something bad would happen, like a spin flip would happen, and then you get a molecule formation. That's bad. But sodium and rubidium turned out to be good in that regard. Lots of collisions before molecules would form. So at the beginning, people thought it'll never work with rubidium or sodium because they're going to form molecules. It's only going to work with hydrogen because you prevent molecule formation. Well, it turns out you can't prevent molecule formation in hydrogen, and you can prevent it in sodium just by getting cold enough. You see, if it's cold enough, then the density doesn't have to be high. And if the density isn't high, the chances of getting a third atom nearby when two atoms collide is very small. You're not going to make molecules.
And having the Bose-Einstein condensate, besides proving the theory, what did it turn out interesting or something?
Oh my gosh, did it turn out to be interesting. So here's another interesting story. When we got it, when I say we, I mean the community, it was Eric Cornell and Carl Wyman who got it first. Everybody was excited. So there was a condensed matter theorist at the University of Maryland who came to NIST. This is in Gaithersburg. The good stuff happened at NIST in Boulder, but we were all so excited. He wanted to calm us down. Basically, he was telling us this is not interesting because we've already done this kind of stuff with helium on an aerogel. The density was low. We got helium basically was acting like a gas, even though it was a liquid stuck to an aerogel. And he said, and we saw. When he says we, he means the experimentalist because he was a theorist. He saw the transition about where Einstein predicted. So what you're doing, it really isn't interesting. So many experiments just started happening one after the other, making atom interferometers by interfering two Bose condensates, studying the interactions of the atoms and how they influenced the behavior of the trapped atoms. Just every week there was a new paper coming out with new and totally unanticipated results from these Bose condensates. So he couldn't have been more wrong about this not being interesting. It just created a whole new direction of research to the point that probably half the people doing AMO physics or more were doing Bose-Einstein condensation. And then that led to degenerate Fermi gases. So Debbie Jin, again out in Boulder, who was working with Eric Cornell to make Bose condensates, said, okay, now it's time to move on to fermions. Completely different idea because instead of having all the atoms in the same state, you would pile up the atoms in what we call a Fermi sea. So you occupy every available energy state up to the Fermi energy with atoms now instead of electrons, and just could do all kinds of marvelous stuff. Her contribution was just so astounding.
Is there some kind of widget that can be built out of Bose-Einstein condensates, like a computer clock sensor, something like that?
Well, we're working on that. So one of the things that we're working on is a kind of an atom version of a squid. A squid is a superconducting quantum interference device.
Like a sensor.
It's a sensor, and it can be used as a sensor for magnetic fields. And people do that. Squid magnetometers are a big deal. And it's used for all kinds of other things. It's used to make superconducting qubits for quantum computers, okay? Mm-hmm. Well, one of my colleagues, Gretchen Campbell, has made a kind of a squid out of a ring trap of atoms with a barrier. That's what a squid does. It has a tunnel barrier. It's called a Josephson junction. She made a Josephson junction in this thing so that it can detect not magnetic fields, but rotation. And this is important because if you can detect rotation better, you can make inertial navigation systems that will work better. And
this is with atoms in a vacuum?
Yeah.
Okay.
Now, we're a long way from making an inertial navigation system. but it's a first step in making devices that use atoms. It's called atomtronics, where instead of electronics, you have atomtronics. And this is, and she made the first atomtronic circuits.
Very cool. Yeah, I think we covered a lot. I don't know if we covered the, kind of once these things got commercialized or, went on to become clocks, where did you shift your focus? Like, what were you already thinking about? Like, was anyone already thinking about quantum computers, or were mostly people thinking about Bose-Einstein condensates? Like, what was the kind of like horizon at that time?
Yeah. So interestingly, the Bose-Einstein condensation was achieved at the same time that the first quantum gate was demonstrated, at approximately the same time as Shor's algorithm, which is what produced all this interest in quantum computing. So yeah.
Well, at the time you were working on clocks, that was like around the time that Feynman came up, if you can attribute it to Feynman, like came up with the quantum computing idea. Was that in the air for atomic physics or not really?
Maybe for some people, but I was not paying any attention to that. I wasn't paying attention to quantum computing until Dave Wineland did the first gate and Peter Shor came up with the algorithm. It really was not.
That's like roughly a decade or so after.
Yeah. So, well, I mean, it was 85 is when we first trapped atoms. So 95 is when all this other stuff happened. Yeah. And no, I'm pretty sure we didn't mention quantum computing in the thing. But what we were thinking about Bose-Einstein condensation fairly soon after that. And well, the other thing, I mentioned it very briefly, optical lattices. Optical lattices are a key thing in quantum computing using atoms now. And so we did a whole bunch of stuff with optical lattices, all kinds of experiments that you could imagine doing in solids with electrons and crystal lattices, but couldn't actually do because you couldn't control the electrons and you couldn't measure them the way we can with the atoms. So we did all these crazy things where we could look at the distribution of atoms in various Brillouin zones. And, this is something that you imagine is happening in electrons and solids, but you're not. We could visualize and take a picture of where the Brillouin zones were.
Wow.
So what's your vision maybe for like upcoming discoveries? We talked about a lot of that luck plays a big role and you need to be prepared and be in the right place in the right time. So if you would have to restart your, for example, grad school, or maybe this is like a good suggestion for young scientists, where is the place to be?
Yeah, that's a good question. I don't know. Look, my favorite American philosopher, Yogi Berra, said prediction is difficult, especially about the future. And I often think if you were to have asked people like Heisenberg and Schrodinger, and Max Born and Pascal Jordan, what is quantum mechanics going to be good for? They would have probably said, well, gee, I mean, just look at it. We can calculate the energy levels of atoms. We can even calculate their transition probabilities. Now, this is fantastic. We might be able to use this at some point to understand chemistry a little better. They would never have thought of the transistor. The transistor changed the lives of almost everybody on Earth. And you don't have transistors if you don't have quantum mechanics. And they never would have thought of that. So there's no way that I can guess what is going to come from what I like to call the second quantum revolution. We've been using quantum mechanics since 1925 to do amazing things. And now we're at the beginning of doing even more amazing things. Quantum computing is using the weird aspects of quantum mechanics. We haven't talked about that. We haven't talked about how weird superposition is and how weird entanglement is. But the second quantum revolution is using these incredibly weird aspects of quantum mechanics to do things that we weren't imagining with the quantum mechanics that led to transistors and smartphones and DVD players and all of that, and all this electronics that's sitting right here in front of us. And the LEDs that produce all these different colors. Think about that.
We have
That's
a new set of
quantum
toys.
quantum materials. And these things have already profoundly affected the energy budget because everybody's using LEDs for lighting, and they're so much more efficient than everything else we had before. So this makes a huge difference in the amount of energy. So all that was part of the first quantum revolution. You didn't need to have superposition and entanglement, at least not explicitly, in order to understand. I mean, it was implicit in just the fact that we have wave functions. But now we're on the verge of doing incredible things where we're using superposition and entanglement in a really fundamental way to make quantum computers, to make quantum simulators. And what is going to come of this? I don't know. I recently read an article, well, it was just maybe a year or so ago. The title of the article was, What Are Quantum Computers Good For? And the abstract was absolutely nothing. Yet. Yet.
Is there just a question, since you spent a lot of your career on precision, right? And precision measurements, is there something that you would like to see measured more precisely?
Yeah, absolutely.
Is there a quantity that needs to get measured more precisely?
Oh, absolutely. And they're already doing it, but they're going to do even better. So one of the things I really want to do is I want to have 2 atomic clocks that are both as good as you can make them, which today is a few parts in 10 to the 19. Okay? But I'm sure in a few years is going to be about 1 part in 10 to the 19. And, I probably won't live that long, but it'll go to a part in 10 to the 20. Okay? I want to have 2 atomic clocks that are based on atomic transitions that are as different as you can imagine. They depend on the fine structure constant completely differently. Maybe it's a molecular transition, so that it depends on the ratio of electron and proton mass, or maybe that's a separate experiment. And then I want to put those things into a satellite that has a very eccentric orbit, either around the Earth or around the Sun. Now, if Einstein's general theory of relativity is correct, the ratio of those 2 clocks is going to stay the same as you go from a very high gravitational potential to a very low gravitational in this elliptical orbit. And we've tested that, but at levels that, are nowhere close to what can be done with these clocks that we have today. And see, one of the reasons that I want to see that is maybe a failure of Einstein's theory there will show us, well, it would definitely show us that the equivalence principle fails. The equivalence principle is the bedrock of general relativity. So if the equivalence principle fails, then we've got a clue as to how general relativity has failed. General relativity must fail, or quantum mechanics must fail, because general relativity and quantum mechanics don't play well together. So one of them has to fail if we're going to have something that encompasses both quantum mechanics and general relativity. Now, maybe that's not possible. Wouldn't that be interesting? So any way this turns out, this is going to be interesting. If at that level you see no change in the equivalence principle, what does that tell you? If at that level you do see a change in the equivalence principle, what does that tell you? And these clocks are capable of doing that.
Oh, very cool.
Wow. I love that idea. It's like stitching the train to put in contact the 2 contradicting theories.
Okay. Yeah, I don't know, unless there's something we haven't discussed.
There's so many things we haven't discussed. I mean, we've mentioned it, but we haven't discussed optical lattices. We really haven't discussed the things we do with Bose-Condensates, but we don't have time. We haven't discussed how quantum computers work and the ways in which they build upon the things like laser cooling and Bose condensation and magnetic trapping and laser trapping, and how you've got neutral atoms that can do one thing better, and you've got ions that can do maybe another thing better. And my idea that maybe the ultimate quantum computer is going to be a hybrid, where maybe you do computations with a superconducting processor and you store information in a neutral atom.
Why do you think that's an interesting architecture?
Well, because neutral atoms are just naturally, as well as ions, are just naturally free of decoherence.
Mm-hmm.
You can isolate them so well
Right.
from their environment. And that's what you want. You don't want to have these just storage qubits having to be error corrected constantly.
Right.
They will have to be done if they're going to be super. You're going to have to do error correction,
Mm-hmm.
even though you're not doing anything.
Right. They just fall apart.
You're just going to have to. Well, they don't really fall apart, but they decohere. Another thing that people don't talk about is that every one of those qubits has to be an atomic clock. That is, it has to keep time, and you have to keep track of the phase of the superposition, and only an atomic clock can keep track of that at the level it's going to have to be. So you don't want to have something like superconducting circuits, which are sitting on a substrate cooled by a dilution refrigerator. So it is not isolated. So you don't,
how do you envision connecting like a neutral atom or an ion?
There's the problem. Connecting them. So the interface, the interconnect, is the real problem.
Yeah.
So it's going to have to be something, of the sort where the neutral atom creates transfers its information as a qubit into, say, a microwave photon, which then travels down a nearly lossless transmission line to a superconducting qubit that eats that microwave photon and uses it to change its state. I mean, something along those lines has to happen. And either it has to happen with extremely high fidelity so that you can error correct it if it doesn't work, or it has to be done in a way that if it doesn't work, you get to try again. And there's a number of ways in which there are protocols for sort of teleporting the quantum information. And so, but that has to be figured out yet. There's a whole bunch of things that have to be figured out in order for quantum computing to work at the level of a fault-tolerant quantum computer that can do a general problem. And I mean, it's not like we have to have that.
How do you see the ion versus neutral atom?
Yeah.
Like, what's the trade-off?
So it's harder to have lots and lots of ions in the same place because
Just repulsion.
Yeah, they have these long-range interactions. On the other hand, those long-range interactions make it possible to have faster gates because they have much stronger interactions, but they're nowhere near as fast as the solid-state system. So I'm imagining that you might have a solid-state processor and an atomic storage because for just that reason.
Neutral atoms are the easiest to scale and keep stable, and then
whether they're that easy to scale, I don't know. I mean. They're probably easier to scale than ions, but I'm not sure. Clever ideas you can you can shield things, so it's not that hard to have a lot of ions in the same place.
Is it mostly like laser limited or field of view limited? Like how many?
I don't really know. I don't really know what is going to be the ultimate limit. I just, heard something. John Martinez was saying that he wants a 1,000,000 qubit processor. So 1,000,000 superconducting qubits. So that's non-trivial. Making 1,000,000 atoms is not going to be easy. But if people are making hundreds of atoms, and the rate at which they're increasing the number is similar to the rate at which they're increasing the number of superconducting qubits. So it's not obvious that that just scalability is going to be the thing that
this is maybe last question. I think it's interesting. Were there some alternative architectures for doing things like lattices or that don't rely on lasers that kind of ended up not being used in clocks, but might be make sense to bring back for computers or other use cases?
Well, it's a good question. I can't think of one right off the bat. I do remember that very early on, we talked about electrons suspended above the surface of superfluid helium as a possible platform for quantum computing. And then everybody forgot about it. And now it seems to be coming back. So
it's like the new is the well forgotten old one.
Yeah. Awesome. Yeah, Misha, unless you have anything,
No, I think
was
it was a
amazing.
great conversation, and sounds like we have more to discuss. Need to visit one more time.
Yeah. Thanks for having us.
Thank you.
Well, there's no way that you're going to compress. I've been working on this kind of stuff for 47 years. So we're not going to compress it into a 2-hour conversation.
Yeah, thank you.
Thank you.
It's been a pleasure.